Hello and welcome to the session. I am Dr. Akshay Kumar from School of Computer and Information Sciences, and today we will be discussing about Huffman coding in this particular session. Well, what is Huffman coding? Why do we need this kind of a mechanism or this kind of a coding system? Well, you all know when we are doing data transmission, specifically when we are transmitting textual data, which basically consists of sequence of characters. Okay. Now, each character has its own frequency, right? And that particular frequency basically determines that overall size of the data which is to be transmitted. All right. So, that character ultimately is to be represented with the help of a code, right. Now, what kind of coding should we use to represent the characters which we are transmitting? Well, Huffman code is typically a greedy approach to compress the amount of data, that is that coded data which is to be transferred. Well, let us assume a typical example of a particular situation, so that we can appreciate how Huffman coding may be used in different situations. So, let us take a data file exists for 100 characters, right, and it is to be transmitted across from a source to destination. Now, how big that particular data file can be if we use different coding mechanisms. However, the important point here is that we know the frequency of each characters. All right. So, suppose we follow a typical option, all right, which is 7-bit ASCII coding. All right. We assume that we are using 7-bit ASCII coding and there are 100 characters, all right, 100 alphabets, all right, are going to be there. Now, those alphabets, okay, I mean they can be different characters, but let us assume they are just alphabets, and the frequency of those alphabets, assuming that the frequency of A is 70, the frequency of B is just 2, frequency of alphabet C is just 5, frequency of alphabet D is 13, and frequency of alphabet E is 3 and F is 7, all right. And we use as option 1 just 7-bit ASCII coding, all right. So, what this coding can be? We have A, B, C, D, E, F, all these alphabets were being transferred, just 6 alphabets, and the ASCII code for these characters are listed over here, and this is 7-bit representation. So, this is for A, this is for B, C, D, E and F, all right. So, these 7-bit codes are there. How many, what was the frequency of A? 70. So, it will be 7 into 70, like that you compute for every alphabet, all right. And what we get, obviously there were 100 alphabets and each of the alphabet is represented with the help of 7 bits. Therefore, we will have 700 overall bits, right, 7 into 100, okay, that makes it 700. We have computed them individually also, and they will also turn out to be 700. So, in total we are having 700 bit. If we send these particular characters as 7-bit ASCII from a particular source to destination, okay, very simple, fine. We can save. I mean, it is not necessary that we just work in this particular situation. We can save because we are just having 6 characters. So, can we put some code to or give some code to this particular thing? How many bit of code is going to be sufficient? because 3 bits is 2 to the power 3. So, we can have 8 representation, right. So, we might just need 3 bits. Okay. So, second option is we coding for 6 characters, which will be just coded by 3 bits. Okay. And these 3 bits can be all zeros, 1. So, A is represented by 3 zeros, B is by 001, 010, 011, 100 and 101. So, these are my bits now. Okay. These are my codes, and the total bits will be required once again 3 into 70, that is what the frequency of A was, like that. So, we can compute the overall number of bits for each character, and total in any case they will turn out to be 300 bits. Why? Because each bit is, or each alphabet or each character is being represented by 3 bits, and there are 100 characters, right. So, there are 100 characters. So, 100 into 3 is overall we need is the 300, all right. So, that sounds okay, all right. So, we have saved from somewhere from 700, we have brought it down to 300 bits. Now, the question is, can we do it better, all right, and that is where Huffman code comes in. Well, the basic principle is very interesting in case of Huffman code. What it does? To reduce the number of bits that are to be transmitted. That is obviously the reason thing which we would like to demonstrate. However, how does it do that? It checks the frequency of each character and represent the characters with high frequency using smaller code, right. So, what we are going to do? Some characters which have very high frequency, can we represent that particular character by lower number of bits, and the characters which have lower frequency, higher number of bits representation or coding is not going to matter much, all right. And the length of the coding of characters therefore, in this particular case is going to be variable, right, because low frequency character will be represented by longer bits, higher frequency characters will be represented by smaller number of bits, all right. So, this particular variable length is another hallmark of this particular Huffman coding, and the decoding of message, however, should be simple. It should not be very complicated, all right. So, and it should be unambiguous also. So, that is what it should ensure, right. So, these are some of the things which we expect in Huffman coding or any coding for that matter. And the interesting fact about Huffman coding is that it compresses overall messages by 70 to 80%. Well, Huffman code, if we are trying to define, since we want it to be unambiguous, right, therefore, the prefix of a code should not be same for the code of 2 different characters. So, prefix of code should be different. Now, that is very interesting, and the example is, for example, if 10 is the code for A, all right, then 101 cannot be a code for B. Why? Because this will become 1010. So, this prefix is going to be the same, all right, and that prefix might result into some kind of an issue, all right. So, this is what is which we want this particular this prefixing should not be the case. So, this ensures that while decoding the encoded message, there is no ambiguity due to prefix of the code, okay, and ultimately it simplifies the decoding process. There are 2 steps basically as far as Huffman coding is concerned. Okay. First, we build the Huffman tree, and then Huffman tree we find the Huffman code for each character using a typical tree traversal method. All right. How do we build the Huffman tree? Well, the algorithm or the steps when we want to build the Huffman tree are basically input is, what is the input needed in case of Huffman tree? The input needed is a set of m characters, and each character basically if we recognize as m, which is a subset of m, has a frequency, and we have denoted that as m frequency. You can denote it in variable, any variable you want, okay. But this is what is that each character has an associated frequency. And the data structure which we use in this particular case is basically it stores all the characters in min priority queue using frequencies as the key. Okay. So, priority queue is the one where we are basically making sure that the minimum, whatever characters has the min priority queue, where frequency is basically the key as far as this particular priority queue is concerned. What we are basically using is basically min heap. Okay. Although we are on one side we are trying to maximize, right, we are looking into the maximum stuff, but we are doing the min priority queue. So, this is very important, okay, and we will see in example why we are using this min priority queue and maintaining it with the help of min heap. Okay. So, we will be making a priority queue with the help of heap. Now, what min heap will be having property? The root of the min heap is having the smallest value, all right, and all the other values are going to be larger than this. So, all the leaves, all the next level stuff is going to be higher than that. So, that property we will be utilizing, and normally a heap takes order log n time as far as insert operation is concerned. This is part of your data structure in any case. Okay. Now, how we are going to build the tree? Extract two maximum nodes x, y from min priority queue PQ, okay, and make a new node z with x as left child and y as the right child. So, x is a smaller node and y is the larger node. So, we are making x and y as the left and right child of this particular nodes. Then replace node x y in the queue with a new tree node z. So, we will be creating a new tree node and replacing it, and the frequency of z is the sum of the frequency of the x and y. So, this new node z, its frequency is going to be frequency of x and frequency of y put together, just added together, and this particular step will be repeated until one node is left in the queue and return this last node the root of the Huffman tree. So, this becomes the Huffman tree. Let us do it with the help of an example. Okay. So, build a min priority queue based on the frequency. So, this is the min priority queue where B is 2, E is 3, C is 5. So, this is where you can see we have a priority queue where minimum is B, next is E, next is C, next is F, next is D, and A happens to be having the highest frequency. So, 70, you can see these frequencies are listed over there also, and these frequencies are listed in this particular case. And initially our queue, which we have named PQ, contains how many? Just 6 nodes, all right. So, this with 6 nodes we are starting this particular situation. Okay. So, this is our starting position where we have built our priority queue. So, this is my priority queue, right, where the lowest min priority queue. So, minimum is here, next minimum, next minimum, next, all right. So, minimum, then from the minimum from the remaining, minimum from the remaining, and so on, all right. So, this is the min priority queue. Okay. So, let us now do the steps. Extract 2 minimum nodes from PQ, make and add Z. So, B had a frequency of 2, E had a frequency of 3. So, B is x, right, That is what we extracted, the minimum x and y. So, these two nodes have been extracted from the min q, obviously they have been removed from there. And what happens then? We create a new node z with x as its x is left child and y as its right child, right. So, B2 E3 becomes the left, B2 is left child, this is right child, and z becomes the, and the weight of z is 5, why? 2 plus 3, all right. So, the frequency of z is basically 5 put together over here, all right, and z is once again reinserted into the q, or just we have kept it here, although it should have been reinserted. So, it will come into this particular position only, all right. So, we have added z back. What next? Now, we once again extract two minimum nodes from the PQ, make and add z. So, this is a new z now, all right, and the earlier z has been picked up, this was earlier z 5, all right. So, this earlier z is now x, because that is what, it is a recursive algorithm. So, this is the left hand side and this is the right hand side, we picked up c, all right. So, what we have picked up? This as well as this, these two we have picked up, okay, and this 5 and this particular stuff is over here and this stuff is over here, what we can see, okay. And we get a new z here with the weight of 5 plus 5, 10. So, this was already 2 and 3 already were there, okay. This particular whole subtree we have already created, we have added this particular new node and we become, we got z as a new z over here. Weight of this particular z is 10. So, when we insert it, we will insert it after f, all right. So, we will be inserting it after f, all right, and this is what is going to, so we next step we will be picking up f as well as this particular z, all right. So, these two nodes will be picked up, all right. So, f was picked up, f is having lower frequency, that is why it is onto the left hand side of the tree, and this z, earlier z was having higher frequency of 10. So, this is onto this particular side. So, now you can see the old tree is appearing completely over here, all right, and overall frequency is now 10 plus 7, 17, all right. So, this is our new z, and this new z is to be inserted. Where it will be inserted? It will be inserted after D13, okay. It will be inserted after D13 in this particular location, all right. So, this once again in the next position what we will be picking up? D13 and Z17. So, Z is basically this entire tree, all right. So, Z actually is this particular entire tree, okay. So, we in the next step we pick up, all right. So, D13 and Z, earlier Z, and this is the new Z now, all right. So, this is picked up as Y, this is picked up as X, all right, and you get overall this particular, this tree was already existing, all right. So, this entire tree was already existing, we have added this x onto the left hand side, okay. So, now the new weight is 17 plus 13, all right. So, this 17 plus 13 becomes 30, okay. Now, this is going to be inserted here only, okay. So, now we have two more, okay. So, this is going to be the last step now, we will make the final tree, and how we are going to pick up our z is, so 30 is towards the left hand side because that is the smaller one, that was the entire tree which we had, and this is our 70 is onto the right hand side. So, we got z as 100, all right. So, now everything is complete. So, our Huffman tree is now ready. Now, this particular Huffman tree, we got to address, we got to convert this particular address, this particular Huffman tree onto Huffman coding. So, how do we do that? Okay. So, finding the Huffman code for each character, How do we do that? Traverse the tree starting from the root node, label an edge connecting to the left child as 0, label an edge connecting to the right child as 1, traverse every leaf node in the tree, right. Huffman code for leaf node character is the sequence of labels on the edge connecting the root to leaf of that particular character. Seems very complicated, but it is very simple when we go through the example. So, this is our Huffman tree or the final Huffman tree which we have created, 100. So, when we move to the left, we put a label 0. Okay. So, we come to 30, we move to the left, we create a label 0. We move to the right, we create a label 1. Move to the left, we create a label 0. Move to the right, we create label 1, 0, 0, 1, right. So, the left you have 0, left you have 0, right you have a label 1, all right. So, now we have completed the label. Now, let us create the coding for this. Now, how to create the coding? So, the coding for, let us say, coding is going to be only for the leaves, all right. So, this leaf, this leaf, this leaf, this leaf, all these leaves we got to go to coding. So, for A, we just need to go here. So, what is the code for A? Just 1, the smallest code. What about B or let us say D in this particular case? It is going to be 0, 0. What about let us say B? Okay. It is going to be 0, 1, 1, 0, 0. So, that is how we reach to B. So, it is 0, 1, 1, 0, 0, all right. Like that E, 0, 1, 1, 0, 1, right. So, like that you can determine the code for each character, all right. And what we have here for A, we just traversed one node. So, the length of the code is just 1, all right. And for coding we just require 70 such characters, all right. For B, 2, obviously B had a very long code, all right, but the prefix is different, all right. So, this you can see that we require 10 bits. We require for C, once again C has a slightly longer code, we require just 20. What about D? D is better, just 2 bits, we got 26, like that. And overall what you see, we just got 162 bits. There is still a large amount of saving from 300 bits which we utilized when we had the fixed length code of 3 bits, all right. So, we have definitely saved here, all right. Let us try to do something, example for coding, right. So, if I want to code, okay, A, B, C, the codes are defined, all right. Suppose the message is A, B, E, F, like that, okay. Then the coded message is going to be, for A we will be replacing it with 1, A once again 1, B happens to be the long characters, E happens to be long 5 characters, F just 3, D 3, like that, and this is going to form my final string. But can I decode such strings? Let us try to see. Okay. So, let us look into the decoding. Now, this decoding of the string is slightly different. Okay. So, let us look into 0, 1, 1, all right, 0, 1, 1, 0, all right, 0, 1, 1, 0, and it is followed by another 0. So, this is going to be B very clearly, this particular character, all right. Next, you see is just 1, okay. So, your character has ended there. So, the next character is simply 1, okay, or next, sorry, bit is 1. So, it is going to be A. Next bit is one other 1, it is going to be A. Okay. Then we starting with 0, okay, that means a new character has arrived. So, 0, 1, 1, okay, and 1. So, 0, 1, 1 and 1 is basically C, very categorically we can read C. This is followed by 2 zeros. 2 zeros, okay, because 0 is nothing, right, only 0 0 is the only character. So, 0 0 is D, thereafter once again 0, okay, once again 0 1 1, okay. So, we get 0 1 1 and 0 1. So, we know it is going to be E, all right. So, like that we are recognizing each character, all right, and finally we get 0 1 0 which happens to be F. 0 1 0 happens to be F. So, we are able to decode our message uniquely as B, A, C, D, E, E, F. How? Once again start from the very beginning, all right, and what we see 0 1 1, 0 1 1, there are this 0 1 1, there is no other way, right. So, this only 3 possibilities, but going on next is 0, all right. So, next is 0 1 1 followed by 0, 2 possibilities left now, all right, and next is 0. So, obviously it is B. So, we have over here we have terminated now, and then we can move to the next one. 1 is the only this particular code, okay, like that. So, this is the reason why we do the no common prefix, and with that no common prefix, although decoding is slightly difficult when we have fixed length code, yet it is unambiguous and it can be done easily. So, what is the time complexity of this algorithm? Well, a priority queue is implemented using a binary min heap, right. So, building min heap procedure takes order n time. The tree is made exactly in n minus 1 times. Since in each step a new node is added, z is added to the heap. When a new node is added, it takes order log n time only. Thus, the total running time of Huffman algorithm on a set of n characters is just order n log n, and n log n is a good order as far as coding mechanism is concerned. So, let us try to summarize what we have covered in this particular session. Huffman code is an approach to compress. So, you can compress the coding to quite an extent. However, coding should be such that there is no ambiguity, okay, and what we are using is variable length encoding, all right, okay, and the prefix have to be kept different to ensure encoding is unambiguous, okay, and the algorithm we have already discussed, and the running time of this particular algorithm is n log n. So, next time onwards, when you are using frequency oriented data transmission of alphabets, try Huffman encoding. With this, we end this particular session. Bye for now.